Okay, thank you very much for inviting me, and thank you to all participants for being here. It's a pleasure to be here, and I'm very much looking forward to talking to you a little bit about Bayesian statistics and about BRMS. So as said earlier, I'm happy to take questions kind of in between. I'm not going to monitor the chat, but I will be notified, and I will kind of give at the right moments kind of the possibility so that these questions can be answered. In my talk today, I will kind of mix it up between some ideas of Bayesian statistics and then how to realize them in BRMS so that the R code is just not out of context, but kind of embedded in a context of where it hopefully makes some sense. Okay, so let's start. And I'm not really sure what it is with Bayesian statisticians, that whatever they do, they kind of have the feeling that they need to introduce the Bayes theorem. So in that tradition, I'm going to do that as well. And so basically the goal of Bayesian inference, which is part of Bayesian statistics, is that we estimate the posterior distribution. That is the distribution of the parameters, which are called theta, given our data, which I call y here. So it's basically the distribution of the unknowns, our parameters, given what we know or have observed, our data. And that kind of, in this ideal sense, summarizes all the information we have about the parameters. And they are, like in classical Bayesian statistics, two primary sources of where that information about our parameters can come from. One is our data itself. So that enters the posterior through the likelihood, which is this distribution P of y given theta on the right-hand side. So it's basically the distribution of the data given our parameters. And it's nothing else than what we optimize a maximum likelihood estimation. Right? So it's kind of, if we were just doing maximum likelihood estimation, we would just use the likelihood. But in Bayesian statistics, kind of we multiply that likelihood with another term, which we call prior, so P of theta, which is basically the distribution of the parameters before having seen the data. So there we can enter all sorts of prior information from prior experience, from expert knowledge, from whatever that doesn't come from our data directly. Then we combine those two sources via multiplication, and to make sure that the resulting function is actually a distribution, that is our posterior distribution, we normalize using the marginal likelihood P of y. The marginal likelihood kind of gets us into trouble in a lot of cases, but we don't need to talk about that here today. So I would like to kind of slightly rethink the Bayes theorem, and first of all, drop the marginal likelihood so that the posterior is just proportional to the product of likelihood and prior. And this product of likelihood and prior is nothing else than the joint distribution of y and theta. That is the joint distribution of all quantities we have in the model, right? So what we basically do when we're doing Bayesian modeling and we're building a Bayesian model, we are writing a joint model of all quantities we have or think are interesting in our specific use case. Some of which are known or observed data, some of which are unknown parameters, but kind of the difference in the sense of what's known and what's unknown is kind of fluent. So for example, if we have missing data, some of what was originally supposed to be observed suddenly isn't observed anymore, so becomes parameters. So in Bayesian statistics, in this thinking of joint priors, what is parameters, what is data, what is known, what is unknown, kind of becomes more loose. And we can think of it more generally as this joint model of everything we have or everything we care about, and then just hope we have enough information in our model so that we get some reasonable information out of that for our unknowns, that is for our parameters. And so I want to briefly start with some personal list of advantages and disadvantages of Bayesian statistics. There may be more, there may be less, so that's kind of just my personal list. So I think we have quite a few advantages. One is that we have a natural approach to expressing uncertainty, and we express uncertainty using probability. That is basically all uncertainty there is in Bayesian statistics, we can ideally express using probability, which I think is quite intuitive. We have the ability to incorporate prior information if we have prior information and if we want to incorporate that prior information using the prior distribution. It's not necessarily easy to kind of take expert knowledge and put that into a prior. There's a whole field called prior elicitation that goes into that detail. But in principle, this is possible. And if we are able to do it, it's really helpful. We have an increased modeling flexibility. That is, we are able to specify and fit much more complicated models, that is, models with more parameters than would be usually possible with other approaches. We get the full posterior distribution of parameters, that is, we get the full distribution of them instead of a point estimate and some approximate measure of uncertainty, such as a standard error in classical statistics. So we get more information for our parameters. And I think the last point is perhaps one of the most nice ones, is that we have a natural propagation of uncertainty. That is, if we are interested in a quantity that can be computed based on our parameters, we can take the posterior distribution of the parameters to obtain the posterior distribution of whatever quantity we're interested in. So suppose we have two parameters A and B, and we are not interested in A and B, but rather in A plus B, or A times B, or A to the power of B, whatever. We can basically take the machinery of Bayesian statistics to propagate the uncertainty from A and B to our new quantity, let's say A plus B, no matter the transformation we do. So that's a quite powerful property that I think like one starts only to fully realize how nice it is once actually working with it. And I think there's one disadvantage, but it's a major one, which is the slow speed of model estimations. So instead of like taking fractions of a second or a second or a few seconds, things may take seconds or minutes or hours or days if we have lots of data in very complicated models. So Bayesian estimation is much, much slower, at least the current ones we are mostly using. And this is the main drawback, which means if we have some, let's say, real-time application, probably we wouldn't use kind of the full machinery of Bayesian statistics. Or if we have rather simple models, but really big data, let's say like linear regression with millions or billions of observations, right? Then we probably wouldn't use Bayesian statistics because it just takes too long. A few millions we can handle, a few more we may if we have like lots of computing power, but beyond that, it probably becomes too much if we are using kind of more exact estimation algorithms rather than approximation. Okay, so before I start with the software part, are there any questions so far?
Yes, there was a question coming in just now. These advantages you talked about, advantages compared to what?
Yes, advantages compared to like what I call frequentist statistics. So basically, usually represented using some sort of maximum likelihood estimation.
And
so that's compared to classical, what people could call classical statistics. Yes.
Another question was that came in was if even MCMC is slow.
Yes.
Yeah, from my own experience, I can confirm this. And the last question was, could you briefly comment on variational methods to speed stuff up?
Yes. Okay. So variational methods are a kind of way to approximate the posterior using some fixed family of distributions. So suppose we could be trying to approximate our posterior using a multivariate normal, right? So that's kind of one standard approach to that, but there are others. So I don't like them much because I care about the posterior distribution and the dependent structure of the parameters. And usually kind of for reasonable complex models where we want to use Bayesian statistics, our posterior distribution is quite far away from the family of distribution we are usually using in variation inference, that is usually some sort of multivariate normal distributions. And as a result, the variation of the approximate posterior we are obtaining using variation inference is usually quite bad for the models I care about. But that's just my current personal opinion on that. It may change in the future, and it may change depending on the model. For instance, if we were to fit Bayesian neural networks, which is like a completely different topic, not part of today, then we may have no other choice, because MCMC doesn't work on this amount of data and model complexity, or it doesn't work with years of fitting time. And so there we may want to use variational inference, but then we only care about predictions. And it may be that, like in a lot of cases, variation inference of predictions is well calibrated and works well, but the variation inference for the posterior doesn't work well. In neural networks, I wouldn't care because I don't care about the distribution of the neural network weights. But in Bayesian statistics, where I'm going to interpret the posterior and its parameters, because the parameters usually have meaning, I care about accuracy in the posterior distribution. And that's, to my current knowledge, usually not sufficiently realized using variational methods. Were there more questions?
Just a sec. Yes, there was a thank you to the answer just now. And will we learn about how to approach a speed up of the estimation, or where we can read up on it?
That's a really, I mean, that's an open-ended topic. So it's not part of today, because, but I'll see if I can address it kind of in the end, if you remind me of that, because like that's like a quite big question, and I don't want to spend too much time on it now. But I'll talk about that in the end if you remind me of it.
Yeah, I'll make a note. Thank you.
Thanks. Good. Okay. So let's start a little bit with the software part. And there's lots of Bayesian software, and I'm just going to focus on two. One is, of course, BRMS, kind of the name and the title of this talk, and the other one is STAN. So STAN is a probabilistic programming language that is a programming language just as R, just as Python or whatever, but focusing on writing down Bayesian models. And kind of there are multiple probabilistic programming languages existing, but STAN is like the one I'm using. I'm part of the STAN development team, and it has kind of currently, I think, the best implementation of the Hamiltonian Monte Carlo samplers we currently have in the world, to my knowledge. But like things are in flux, so that may change. And the fact I'm talking about STAN is because BRMS uses STAN behind the scenes. So BRMS is basically an R interface to the probabilistic programming language STAN. So if you have ever used BRMS or will use it in the future, you will use STAN behind the scenes, even if you may not necessarily notice that you do. So I don't want to talk about STAN in detail, but I just want to show you real quick how the STAN language looks like on a simple example of linear regression. So in STAN, the STAN program consists of several blocks. There are more than three, but the three main ones are data, that is where your data comes in, that you kind of pass to STAN, parameters, that is the variables you're going to estimate, and model, where you basically put data and parameters together so that the data informs the parameters through your model. If we were to like specify linear regression, we need a couple of data. For example, we need the total number of observations, which I'm calling n here, and it's an integer with lower value of 1, because we would need at least one observation to do anything sensible. We need a response variable, that is the variable being predicted. I call that y, it's a vector of length n. We need a number of regression coefficients, I call that k, and we need a predictor design matrix, which basically contains our predictor values as columns. And kind of in the columns are the predictor variables, and the rows are the observations. So that's one way to realize linear regression. As parameters, we of course have the regression coefficients. I call them b, and we have some residual standard deviation, which I call sigma. It's the real value with a lower boundary of 0, because standard deviation needs to be positive. So what you see here is then statically typed. So you have to define which type each variable is before using it, which is kind of which you're probably not used from R, because in R you can just assign everything to everything, and it usually works. In Stan, you don't, but the advantage is you can really read through the Stan program without having seen the data because everything is statically tagged. In the model block, we put stuff together. So first we are creating our predictor term, which I call mu, simply by x matrix multiplication b. So that's our predictor term. We specify a prior, for example, on sigma. So this is our prior information on sigma with an exponential prior and rate 0.1. I just chose that for an example. And then in the end, the last statement is basically our likelihood. That is, we call in linear regression, y is normally distributed around our linear predictor mu with a standard deviation sigma. And as our Stan is vectorized, because like y is a vector and mu is a vector and sigma is a real value. So by y not distributed normal mu sigma, we're basically telling Stan to do that for every single observation. And you will see that like in lots of aspects, Stan is actually also, among others, inspired by R. Okay. But of course, like topic of today is not to fit models in Stan. So we're going to use one high-level interface to Stan, which is BRMS. So it stands for Bayesian regression models using Stan. The idea is that we specify Bayesian models via an extended R formula syntax. So when you are familiar with R formula syntax, you can use that in BRMS as well. And I've extended it in various ways so that it's more powerful for the stuff that BRMS can do. We internally write the Stan code that is readable yet fast. That is, you can just use BRMS to create Stan code and look at the Stan code and go from there. But of course, BRMS then also fits the model. So you don't need to look at the Stan code if you don't care about it. So whenever I need to kind of have a balance between readability and speed of the sampling, I'm focusing on speed. That is, there are parts of the Stan code of BRMS that is less readable because it's more efficient to sample from it, or to fit the model, basically. BRMS provides an easy interface to defining priors. Perhaps I would say it provides an interface for defining priors, and whether it's easy or not certainly depends on the perspective. One other important part is that it facilitates post-processing. That is, it's not only about estimation of the models, but to create summaries, to create predictions, to create nice graphics, to create model comparisons. Whatever you are interested in the end, we have some like nice functionality for post-processing so that you don't have to leave BRMS to do all sorts of things you may want to do after having fitted your models. And so just to give you an idea of what happens behind the scenes with regard to Stan code, suppose we have some more complex, like not linear regression, but a little bit more complex model. Then this is the kind of Stan code that BRMS generates. I'm not going through the details. I'm just showing you there's a lot of stuff going on. So that's page 1, data and some transformed data, then parameters and some transformed parameters, and then like lots of models and some other stuff. So this kind of, if you were writing this kind of model here, it's a simple multi-level model yourself in Stan, it wouldn't look exactly like this, but like BRMS writes it that way because it's easier to write it kind of via machine that way, and it's more efficient. But I want to show with that is kind of when you fit more complicated models in Stan and want to make them efficient, it may get a little complicated, but BRMS does all kinds of things for you if you're staying within the framework of models that BRMS supports. Okay. So before I continue with the next topic, are there more questions?
There were no questions.
Great. Okay. So now I want to like go through some ideas that I follow when I'm analyzing data, and I'm going to use BRMS to kind of showcase the situation. So first of all, and this is highly related to multi-level models, is we should think about the data structure. That is, we should think about how our data is structured and how this structure should be reflected in our models. That is, for example, if I have multiple observations from the same class of students, that is, we have observed multiple students from the same class, those students will be dependent on each other because they're coming from the same class, they're sharing the same classroom, the same teacher, and so on. So I want to reflect that structure in my models. And of course, we could go further if we had observations from multiple classes within the same school, right? Those classes were dependent on each other because they're from the same school and so on. So basically, in most observational and in nearly all observational and in most experimental data, we have some advanced data structure, some hierarchy, some complicated dependent structure in our data that we want to reflect in our models. And one way to do that is to use multi-level models. So I'm going to illustrate that using a simple example. So this is an example I like. It's the sleep study data set from the LME4 package in R, and it's basically about the effects of sleep deprivation on reaction times. And here we see kind of a selection of 18 subjects, and we see how the average reaction time changes over 10 consecutive days, from 0 to 9, where we had 9 days of consecutive sleep deprivation, where the participants slept only 3 hours or less per night. And if you ever like have sleep that few hours per night over multiple nights, you know, you're getting very tired, and for most of us, reaction time becomes slower. For instance, subject 3 and 8, the one on the top left, it starts at 250 milliseconds on average at the first day, and it kind of ends at about 500 at the very end. So they became quite slow through those 9 days of sleep deprivation. But there are huge differences between subjects. For example, subject 309 is quite quick at the start and doesn't seem to be affected by sleep deprivation, at least when measured using a simple reaction time task. And there are kind of all sorts of in-between subjects. And of course, the structure of the data, there is multiple observations per person, is something we want to reflect in our models to accurately kind of account for the data structure, to accurately account for the uncertainty, to have some nice and well calibrated estimates, no matter if we do that in Bayesian or frequentist or whatever way. So let's ignore the structure for now and just fit a linear regression model. For example, we could like fit that linear regression model on each of them and would get like a linear regression for each of them. But of course, we could also say, I don't care about the individual subjects. All I care about is kind of the average reaction time increase through the days of sleep deprivation. So I could, in other words, just fit a linear regression model, ignoring that we have multiple observations per person, and basically just say we have, like in this case, 180 conditionally independent data points, without recurring to the fact that some of those data points are from the same person. So let's start to fit a simple linear regression in BRMS. So after having loaded BRMS in R, we use the BRM function as the general interface to BRMS, to Bayesian multi-level models. So whatever model you specify and you want to fit it, use the BRM function. And we are, as said, using our formula syntax. That is, our response variable is on the left-hand side of the tilde, and our predictor variable is on the right. So in this case, reaction is our response variable, and we're going to predict it using the days of sleep deprivation in this data set. We're using the sleep study data set. Of course, this completely ignores the multi-level structure for now, just to get started. And then after having done that, we can do a lot of stuff. And a method I want to highlight here is the conditional effects methods. It basically provides a graphical summary of the relation of predictor and response variables. And what we see here is that kind of on average, we start with like about 250 milliseconds at day 0, and then go to roughly 350 or whatever at the 9th day, or the 10th day rather. But we, of course, completely ignore the multi-level structure, the person dependence in our data set. So let's not make that a mistake and correctly account for this dependency structure. In other words, we're going to fit a multi-level model with one grouping factor, which is the subject the data observation belongs to. So I want to like specify now a varying intercept varying slope model. That is, I want to specify that the intercept, that is the y-intercept of the regression, varies across subjects, and the slope with regard to days varies across subjects. So we had seen that this makes sense in this model, in this graphical representation here, that people started differently at day 0, and they also reacted differently to sleep deprivation over those consecutive days of sleep deprivation. So we want to model both as varying across subjects. And the syntax BRMS uses is, in this simple case, identical to the syntax in the LME4 package, or for that matter, in a lot of other multi-level packages in R. That is, if you want to add those varying coefficients across a grouping factor, you're writing stuff in brackets, and you're separating in those brackets the predictors, 1 plus days. So 1 is the intercept, days is the kind of slope of days, by the grouping factor, which is subject by this pipe vertical dash thingy. So the whole formula is basically, we are predicting reaction time using a global intercept 1 plus a slope of days, also global, plus some subject-specific intercept and a subject-specific slope of days. We could, if you're familiar with our formula syntax, we could also just ignore this 1 plus, and then we would still have an intercept implicitly. I just wrote it down here to make it very explicit that there are intercepts being estimated. So once we have specified the formula, we can again pass that to BRMS, fit the model, Stan is used behind the scenes, and then we're going to get kind of this plot, which again still tells us the average effect of sleep deprivation across over the days on the reaction time. But this time we have accounted for the fact that each 10 observations were belonging to one subject. So we have accurately accounted for the data structure, and thus our uncertainty estimates, which are represented here as 95% credible intervals in the gray lines, are more uncertain because we accurately took the uncertainty structure of the data into account.
Okay. Question.
Questions?
Yeah.
Please.
Can you exclude the global intercept and the global slope?
I mean, yes, you can, but usually I wouldn't recommend it. So the random or the random or varying intercepts and slopes, generally the varying effects, are generally most sensible if there's a global intercept and slope present, but syntactically you can exclude them. Yes.
And another question came up. Is the data object given to BRM structured similar to the list given to RStan?
No, it's a data frame. So it's a data frame where your columns are your variables, for instance, reaction and days here and subject, and the rows are your observations. So BRMS expects data frames or will transform everything you pass there to this kind of data frame structure.
Then another question was, what are the distributional assumptions for the residuals, global and group?
So here, now that we didn't specify anything, we assume that there is a kind of, the likelihood is normally distributed. So basically we have like normally distributed errors, but of course we're going to change that. I'm going to illustrate that in a second. So BRMS supports a lot of different likelihood options or prior options, but default is normal likelihood.
And the final question was, is there a function to provide the raw Stan program executed behind the scenes?
Yeah. Yes. So if you fit the model, you use the Stan code method, one word, to extract the Stan code. And if you just want to get the Stan code without having to fit the model, you're using make_Stan code.
Wonderful. That's it.
Great. Okay. So now that we have thought a little bit about data structure, let's think a little bit about distributions. So let's think about the distribution of the data first. So we should think about the likelihood, in other words. So I'm using now another example, which is the kidney data set. It's basically the kidney data set is in part of BRMS. and it basically models or contains data about the reoccurrence time of kidney infection in like a couple of patients. So time is our recurrence time until this kind of infection occurs again, and we have multiple predictors, two of which are age and sex. The details don't matter too much here, but what matters, of course, is that our response variable time kind of can by nature only be positive because it needs to be the recurrence of the disease needs to occur after the disease occurred first. So time must be positive. But let's suppose we ignore that fact and predict time using age and sex, using family Gaussian, that is using a Gaussian or normal likelihood. We then fit the model and then evaluate the fit of the model to the data. And one way we could do that is to use so-called posterior predictive checks, or short PP checks. What they basically do is they compare the distribution of the response variable y of the observed data to the predictions of the model. So in other words, what the model would predict in terms of response variable after it has been fitted. And as a kind of rule of thumb, if a model is even remotely reasonable, the marginal distribution of the observed responses y should be similar to the predictive responses y rep of the model. And if that's not the case, there's probably a big problem with the model because it doesn't even predict the response variable marginally right. And so suppose we were ignoring the fact that time is positive, but still using a Gaussian likelihood, and then we are kind of using a posterior predictive check. What we see here is that the model doesn't fit at all. And in particular, we see that the model actually makes negative predictions. So y rep is are the responses predicted by the model, and a lot of which are actually negative. So we have like 10 repetitions of that ECDF, of the cumulative distribution function line, to reflect uncertainty in those predictions. And we see a lot of those predictions are actually negative, which of course cannot be because time only needs to be positive. And as a result, also because that model predicts so badly, we also shouldn't trust its inference. So we shouldn't trust its coefficients on age and sex. So we shouldn't trust inference on other things because the predictions are so off. So if we had a model that like fit the data well, it didn't mean this model would be great, but at least it wouldn't be as awful as our Gaussian model on that time data. So we should think about what likelihood we should be applying, and let's use something else. For instance, we could choose family gamma log. So we could use a gamma distribution for our time data with a log link to make sure predictions are positive. There are lots of different choices in BRMS, and you can check the documentation, but that would be kind of a rather simple example. And if we do that and fit the model again and look at our posterior predictive check, we see that now the predicted responses overlay the observed responses quite nicely. That doesn't mean this model is great, but it doesn't mean it's not totally awful. So we should think about what kind of distributions we are applying to our data. Okay.
Well, there was a quick question about PP check, the function. With PP check, can we measure how good our predictions are?
What does it mean, how good our predictions are? There are like a lot of different metrics.
That's not specified.
Okay, so then I continue, but once it's specified, I'm happy to answer it because that's like a very big question. It's a good question, but it's like right now for me too big to answer.
I'll make a note.
Good. Of course, we should be thinking about the likelihood, that is the distribution of our data, but we should also be thinking about the distribution of our parameters before having seen the data. In other words, we should be thinking about the prior. So let's assume we are kind of generalizing the model we just had, but now specifying a prior distribution on our regression coefficients. So I'm using that, doing that with a prior argument in BRMS. And by default, if I'm just specifying a prior, I'm going to put that on regression coefficients. And here I chose as a prior for the coefficients of age and sex, a normal distribution with mean 0 and standard deviation 0.5, right? So intuitively, I would say that looks quite narrow. Yeah? So we're kind of very narrow in what we expect about these coefficients. But when we now go ahead and actually check what kind of data the prior implies, things get really awful. So in other words, we're doing a prior predictive checks. That is, we're not looking what the model predicts after having seen the data, so after having obtained the posterior, but we're doing prior predictive checks. That is, we're just looking what the model would predict based on the prior without having seen the data or before having seen the data. And here's like one example of how that's plotted. So on the x-axis is the log observed response, log y, and on the y-axis is the log prior predicted response, y rep. So remember, this is on the log scale, and what we see is basically that that y rep is around like 4 orders of magnitude bigger than the observed y. Like, so it's completely off. We are predicting way too big things, although we actually thought that we were using kind of only very narrow priors. And the reason is basically that we are working on the log scale because we were using a gamma log model. That is, after exponentiating, things explode quickly. And what is more, age is specified in years. So coefficients of 0.5 with an age range of, say, let's say 10 to 80 years suddenly makes a really big difference. And so the point I want to make here is that we should be thinking about prior distributions. When we know or hope that the data contains enough information to get reasonable estimates, then we can go with the default priors and BRMS, and we don't care for that. But if we have very complex models and we have a feeling that there isn't enough information in our data to inform the posterior distribution, or if we explicitly have prior knowledge we want to incorporate into our model, we need to think about the prior distributions. And in models that use anything else than kind of a linear structure, specifying prior distributions that are reasonable is really, really hard. So that's like an active area of research that I'm also participating in on like how to specify prior distributions appropriately and, most importantly, intuitively, so that people without like being expert statisticians being able to specify reasonable priors. Okay. More questions so far?
Yes. There was a follow-up to the PP check question.
Good.
More precisely, is it a tool to check model predictions roughly? And it's noted that the person shouldn't have used the word measure. But the person is interested in goodness of fit measurements.
Yeah. So it's a rough graphical visualization, and you can use different types of the posterior predictive checks. Most posterior predictive checks are marginal. That is, they are comparing the marginal distributions. Note that the marginal distributions may be quite similar, although kind of on an individual level, predictions are super off. So it's just like a first rough check. If things go roughly well, and when we want to move forward, we need to actually compare predictions on an individual observation level or on groups of observations, or we need to, like, on that basis, compare different models and see which of them predicts better. And then there are also other aspects, such as on what data we are predicting. For example, by default, posterior predictive checks do in-sample fits. So they're basically checking predictions of fit to data we have used to fit the model on. And it's easy to like get perfect in-sample predictions if we include kind of as many predictors as we have observations in the model. So if we really care about like predictions, we should be caring about out-of-sample predictions. That is, let a model predict data it has not seen before. And all of that things are possible in BRMS, and we could tweak the PP check method to also do that by specifying new data. But I am using PP check as the first rough check, and everything else then is used by means of other methods. It's done by means of other methods.
Thank you. There was one more question. Does BRMS use simulation like MCMC or numerical approximation?
Yes, I should have said that earlier. Sorry for that. Yes, it uses MCMC. So STAN has multiple algorithms, but most importantly, and like used 99 point something percent MCMC, specifically Hamiltonian, like some adaptive version of Hamiltonian Monte Carlo. BRMS also supports the variational inference algorithms supported in STAN, but as things currently stand, I wouldn't use them because they are, to my understanding right now, not reliably enough for complicated enough models. So it's always using MCMC sampling, that is using samples to represent the posterior distribution. And for example, if we look at this posterior predictive checks, or rather at that one, we see here we had those 10 light blue lines of kind of predicted responses, and each of those light blue lines corresponds to one posterior sample. Here we have plotted 10 posterior samples, but by default we're going to have 4,000. Of course, the user can change that, but we're not going to plot 4,000 lines in that plot, so we are restricting ourselves to 10 here. More questions?
Just a small clarification question just came in general. Y, as in the letter Y, is the data and theta the parameter, right?
Yes. Good. Okay. Thank you. I'm very happy to get so many questions. Usually I have to like force people to ask questions, but not today. That's great. So next thing I want to talk about is some extensions of standard multi-level R formula syntax that I incorporated in BRMS to make it more powerful. So in BRMS, we can, what I call, add kind of some addition terms to the left-hand side of the formula that is to the left-hand side of the tilde. So for example, if we have censored data, that is kind of some observations are censored if we have just observed them to a certain point and but we didn't know when actually kind of a certain event occurred. So for an example, that was badly explained. So let me explain again. So in the kidney example, some participants kind of initially had the kidney disease, but then they didn't have a reoccurrence of the kidney disease. So during the whole time of the study, they didn't have any reoccurrence. They may still have that reoccurrence later on in time, but we had to stop the study. So we only know the recurrence didn't happen in the time interval of the study, but it may have happened later on. In other words, some of our observations are censored because we only know the event, in this case, the recurrence time, will happen in the future, but we don't know when exactly. So this is additional information on our response variable. There are different kinds of additional informations, for instance, censoring here, weighting, truncation, certain other kinds of things we may want to use, that all complement the information in the response variable itself. And those kind of pieces of information you can pass in BRMS using this, what I call addition term syntax. So after the response variable, you're using this pipe thingy, this vertical dash. Then you're specifying the function that you want to use. Here for censored data, we're using the sense function, and inside the censored sense function, we are specifying the variable that contains the relevant information, in this case about censoring, and in the kidney example, this variable is called censored. So for example, for our purposes, relevant here is that some observations are right censored. That is, we know the time, the recurrence of the kidney disease didn't occur until a certain time, but it may occur later on in time. And so there are different kinds of these addition terms, but all of them can be specified on the left-hand side of the formula following an initial pipe after the response variable. Okay. Are there any immediate questions with regard to that topic already?
No questions at the moment.
Good. Okay. Then I want to dive kind of into a different area of BRMS, which is the modeling of unknown nonlinear functions. So what do I mean by that? So sometimes we have, if we have like modeling nonlinear functions, we have a quite clear idea of how the functional form looks like. And then we could also specify that in BRMS, but I'm not going to talk about that today because that goes into too much detail. But in a lot of cases, we just assume that there is some nonlinear relationship between variables, but we don't know the exact functional form. Instead, we want the model to find out itself how this nonlinear functional form looks like. So we can think of that in terms of this following simple equation. So y, our response variable, is equal to f of x plus epsilon, where epsilon is some error term, and f is some nonlinear function, and x is our predictor. And if we model unknown nonlinear function, we don't know the functional form of f, but instead we have to let the model figure it out itself, how f exactly looks like. And there are various approaches to that. Two very general ones that are supported in BRMS are splines and Gaussian processes. So in splines, very briefly, we represent our nonlinear function f of x using a sum of basis functions bj, which could be like a lot of different potential functions, each time multiplied by a regression coefficient. And if we just add up enough of these functions, in this case uppercase j of these, then we make the spline flexible enough so that it can fit kind of a lot of different smooth functional forms. Of course, this is quite prone to overfitting because it is potentially so flexible. So we need to make sure that those coefficients beta j that correspond to our basis functions kind of are not arbitrary, but are in some sort connected and regularized so that they kind of don't blow up. So what we do, or how we can represent splines, that's one way to represent is that we say in a Bayesian setting, those coefficients beta j come from a joint distribution with some hyperparameters lambda. So all of them are coming from the same distribution, and those hyperparameters lambda are also estimated from the model. So in a sense, we can represent splines actually as multi-level terms. This is the internal representation used by BRMS. And those regularized splines using this kind of multi-level structure make sure, at least help, that we don't overfit too much using splines. So splines are really complicated, and I wouldn't claim that I understand all of the details of splines, but they are really good packages in R, most notably the MGCV package that handles splines quite well. And BRMS uses MGCV behind the scenes to set up all the mathematical stuff with regard to splines. But all what the user sees is if you want to fit kind of this nonlinear function of x using a spline, all you do is rep x in S. So basically y tilde sx plus additional terms means let y be predicted by a spline of x. There are lots of different options of splines, but like the default ones is just S of x. The second kind of very general approach to nonlinear functions are Gaussian processes. And it's kind of an abstract thing that we could say that a Gaussian process is a prior across functions, whatever that means. So we're basically saying that kind of our function values come from a multivariate, like a very big multivariate normal distribution with mean zero and a function that defines our covariance matrix of those function values. And there's like lots of details of Gaussian processes, not the topic of today, but if you want to fit Gaussian processes, or alternatively also approximate Gaussian processes that have some other advantages, and we can just write GPX, and then we're going to fit a Gaussian process of X to predict Y. Again, different options you can specify there, and you can look in the documentation of the GP functions to see some of these options.
Paul, there was a quick question about the splines, the S-splines.
Yes.
Is the number of knots in the splines defined using the MGCV cross-validation?
It is defined using MGCV. So whatever MGCV uses as a default spline, as default number of knots and as default knots for the given spline basis function, this is what BRMS will use.
Thank you.
By default, you can change it.
Just another question. Does BRMS support a smoothing spline model with random smooths across groups?
Yes. Yes-ish, I'm going to elaborate. So I understand the question in the following way. So if we go back to our linear multi-level model here, so we had like a kind of varying linear effects for each subject. But of course, we could also say each subject should have its individual, their individual spline, right? So, and that kind of, we are kind of using a multi-level spline model. I understand it that way. If I understand it incorrectly, please correct me afterwards. Yes, that's supported. There is a certain spline basis function in MGCV that does that. But right now it's super, super duper slow in BRMS because MGCV creates really sparse matrices, and sparse matrix algebra and STAN is not yet very fast. In fact, I'm using dense matrix multiplication still here, but kind of help is underway. In some of the newest updates of STAN, we will have much more efficient sparse matrix algebra. And then I hope, at least, that also those multi-level spline models will be much faster in BRMS.
There was just one more question here. Would a multi-level Gaussian process model require partial pooling of the covariance matrix parameters, or are you describing all Gaussian process models as multi-level?
Okay, I didn't intend, okay. So I didn't intend to describe Gaussian processes as multi-level models. Here, of course, they can be seen that way in a certain kind of way, but so with regard to the former part of the question, BRMS doesn't support kind of multi-level Gaussian processes in the sense that we have partial pooling over the covariance matrices. I have thought of that, but I didn't get a quite nice specification of that yet. I think there's an issue on BRMS GitHub for that. So that's not yet supported there. We have this kind of partial pooling over multiple Gaussian processes because I'm not yet sure about the right notion of such kind of model. Not sure if that answers the question, but I'll try.
We'll do so now. And one final question here. What is the default basis set for smoothing splines in BRMS? Cubic splines or thin plate splines?
Thin plate splines. MGCV uses thin plate splines by default, and that's what BRMS uses as well.
Paul, is this a good time to take a 10-minute break? We've been at it for about an hour now.
That's good. So
So welcome back. We just had a quick break. If you're watching this on YouTube, feel free to continue enjoying the talk. Paul, you're muted.
Thanks. Okay, let's try again. Now can you hear me?
Yes.
Yes.
Good.
Paul, there was a quick question, if we can just throw that in. Does BRMS currently support survey weights, for example, PISA weights?
It supports weights. So if you have weights from somewhere, you can weight it. But I mean, it goes into a lot of detail about survey literature. I personally prefer, instead of weight, I prefer using post-stratification, which is basically realized through multi-level modeling. And we have like to illustrate how to do that in BRMS in a complicated setting, we have like a paper that's actually like not specifically about Bayesian methods, but you can see all the details there. It's you can see it on my webpage. It's from Marta Koliczynska, and it's about trust in political institutions in Europe. And if you read the paper and look at the appendices of that, there's like a lots of stuff actually where we used plus stratification, and in specific parts also survey weights in BRMS, or weights in general.
Thank you.
Good. Okay. So now I want to apply splines like in one simple example, or like one actually more complicated example, which is about modeling housing rents in Munich. So basically what we want to do, we want to predict the rent per square meter of apartments in Munich as a function of the area of that apartment and the construction year C for construction year. And of course, like we have, like at least I don't have any idea how kind of the area of an apartment or the construction year should be related to rent per square meter, especially not since we would expect some nonlinear effects of these two predictors on rent per square meter. And we are also no idea how they interact. So we're going to fit a two-dimensional spline that is S area, comma, year C. So we have a two-dimensional spline of area and construction year. And in addition, in this model, like our apartments come from multiple districts of Munich. And of course, like, I mean, Munich is like is very expensive regardless, probably, but there are some districts which are even more expensive than others. So we want to take that into account. So we're adding a varying intercept to the model using one pipe district. And then we can fit that in BRMS. This model kind of is already kind of nice, but I want to go one step further and not only predict kind of the mean rent per square meter by area and construction year, but I also want to predict the variation of the rent per square meter by area and construction year and district, because it's very well possible that for some areas like of the apartment or construction years, there's just much more variation in rent per square meter than for others. So we want to predict both the mean and the variance or the standard deviation of our rent per square meter. And I call that distributional regression, because we're not only predicting the mean or some other measure of central tendency of our response variables distribution, but we're going to predict multiple aspects of that. For instance, the mean, which I call mu, and the residual standard deviation, which I call sigma in normal models. In this housing rents in Munich's example, we're going to predict both the mean and the residual standard deviation, sigma, by a two-dimensional spline of area and construction year, and by each time a varying intercept of district. So we have two varying intercepts of district, one for the mean and one for the residual standard deviation. And if we want to make them to be correlated, we have to use what I call ID syntax. So if we didn't specify something just like those varying intercepts, like in the FitRed1 model, those two intercepts would be modeled as uncorrelated, but of course they may very well be correlated. And the way we realize that is that we are not using not one, but two pipes, and then putting a symbol between the pipes, for instance, D here, but it literally doesn't matter what we put between there. We could say, I don't like Bayesian statistics, or I don't like waiting for my Markov chains to converge. And it would work as long as the symbol in between is the same. In this case, this lowercase d is the same. And when we do that way, basically, those two varying intercepts of district will be modeled as correlated, even though they are appearing in multiple formulas. That is, like BRMS allows very complex models with multiple formulas if we have multiple distributional parameters we're going to predict. I'm finishing that example. I'm sure there are questions and I'm going to answer them in a second. So we also fit that model, and then we are going to illustrate our splines, and kind of one way to illustrate the splines themselves is using conditional smooths. So let's look at the results of the spline on the prediction of mu, that is on the prediction of the mean rent per square meter. So here brighter values indicate higher rent per square meter. Darker values indicate lower rent per square meter. I obscured the axis because it doesn't matter here. So what we see is that there's like particularly high rent per square meter for like for very small apartments, like below 40 square meter, and for like very new or quite new-ish buildings with construction years in 1980 to 2000. So that was new back then when the data set was created, but there's lots of space, especially for bigger apartments and older apartments, that is like a lower construction years, older construction years, where the rent per square meter is comparably smaller. But of course, we did not only model the mean rent per square meter, but also the variation or the residual variation of that, and that's the spline for this. So we see there's particularly high variation in the rent per square meter for very small apartments of very low buildings, so in the bottom left or in the bottom right, while there's comparably little variation if we have kind of average areas with some construction years around 1960s. So we get a lot of additional information by not only modeling the mean, but also by modeling the residual standard deviation, sigma. Okay. Yes, are there questions about that?
There was one question in the chat a few minutes ago, and the question was, is sigma square the group level variance?
No, it's the residual variance of the likelihood. That is, sigma is the residual standard deviation of the likelihood, and sigma square is the residual variance of the likelihood. The group level variance would be what I call kind of the variance of standard deviation in multi-level terms. So in that model, we would have group level standard deviations or variances of the districts through those varying intercept terms, but there would be something else than the residual standard deviation sigma, which is a parameter of the likelihood. So a normal likelihood not only has a mean parameter, but also a standard deviation parameter, and sigma is that standard deviation parameter of the normal likelihood.
Thank you. And another question that just came. What package is used for those visualizations?
A ggplot. Or ggplot2, rather. Yeah.
Yeah, that's it for the moment.
Good. Great. So I think that's, yeah. So this is going to be the kind of the last specific topic I'm going to talk about, and then we can decide on whether I take more questions or I walk through some more, like one more smaller case study. We'll see about that. So one thing I talked about initially when answering a question is kind of how do we actually compare models, or earlier, how do we actually evaluate model fit or predictions? And of course, we can evaluate model fit or predictions using in-sample predictions, that is, predicting data that the model has seen, like that the model was fitted on, or out-of-sample predictions, that is, predicting data the model has not seen. The problem, of course, is how do we estimate predictions for new data, that is out-of-sample predictions, without actually new data, because we have used all the data sensibly in our model. And one kind of the natural way to answer that is using cross-validation. And in cross-validation, we are splitting our data set in two parts. One we call the training data, that is the data we fit the model on. And the other is the test data, that is the data that kind of we evaluate model fit on. Notably, the test data was not seen by the model during fitting, so it's basically really new data for the purpose of predictions. Of course, if we just do the splitting into training and test data once, our out-of-sample predictions may be quite biased, just because we happen to kind of unluckily select a certain kind of training and a certain kind of test data set. So in cross-validation, we not only do one data split, but we do a lot of data splits. So and the first formula on that on this page, basically this PYS given Y minus S means YS is our test data, so the new data, and Y minus S is all the data not in our test data, that is the training data. So when we're doing cross-validation, we're interested in the posterior predictive distribution of the new data, YS, given all the old or training data, Y minus S. And to make sure we are not just being depending on that specific S and minus S data split, we're going to do that for a lot of different data splits. Then we sum over the results. So if we take this posterior predictive distribution of YS given Y minus S, take the logarithm of that, and then sum over a lot of these different training and test data splits, we are getting to some measure which we call expected log predictive density, or short ELPD. So kind of a detailed description of kind of out-of-sample predictive performance and cross-validation is kind of out of scope of this talk, but the ELPD is one central measure to measure out-of-sample predictive performance and cross-validation. Other measures could be kind of mean absolute error or root mean squared error, RMSE. We prefer the ELPD because it kind of better takes the whole posterior predictive distribution into account rather than just primarily measures of central tendency. So this kind of cross-validation in specific ways is automated in BRMS. The problem we have usually with cross-validation is we have to refit the model a lot of times. So each time we have a new data split, we're going to fit the model on the new training data, which doesn't matter if we have like each model, like the model fits like in 1 second or so. But if our model takes, say, 12 hours to fit and we have 100 data splits, that's not going to work at any reasonable time. So in other words, we would like to do approximate cross-validation. That is, kind of do some sort of cross-validation, but without actually refitting the model and just using the one single global model on the full data to approximate the specific kind of cross-validation procedures. That doesn't work well generally, but it works for leave one out cross-validation. In leave one out cross-validation, each time we leave out only a single observation, then fit the data on all other observations and predict that single left out observation, and we do that for each observations. And this can be approximated quite efficiently because the gap between the full model with all observations and the model without one single observation is quite small. So we can bridge that gap efficiently using importance sampling to basically have some out-of-sample approximate leave one out cross-validation without actually having to refit the model. And this is conveniently implemented in the LU package with the LU function. I know it's an unfortunate name. I didn't came up with it, to evaluate this kind of out-of-sample predictive performance and obtain kind of an ELPD estimate of out-of-sample predictive performance based on leave one out cross-validation. So we can do that for our second model, FitRan2, which kind of gives us that output. I'm not going into the detail yet, but like one aspect I want to highlight is that the second matrix we have in the output about Pareto K diagnostic values tells us something of how good the approximation worked. And if it didn't work well, we're going to get some warnings. So as a rule of thumb, I'm happy with using approximations as long as the approximation method tells me when its results shouldn't be trusted. And the kind of approximate leave one out cross-validation we are having implemented in LU is in the way that it tells us very well when it shouldn't be trusted.
Quick question here regarding the LU functionality.
Yes.
I believe the LU package requires you to include a log likelihood in your STAN model. Do all BRMS models include this?
They don't include it in the STAN code, but all BRMS models have kind of inside BRMS have log likelihood functions that can be used. So as a user of BRMS, you don't need to worry about it.
A quick follow-up from me. Does that also cover the command stan-r backend?
Yes, because the backend just relates to how the model in STAN is fitted. But the log likelihood functions are not defined in STAN, they're defined in R. So they're independent of the STAN interface.
Then there was another question here. Is it possible to use other scoring rules in BRMS than the log score to measure the predictive performance?
So right now, Lou for most of the for a long time, Lou did only support ELPD, but there has recently been a pull request to support other kind of measures, for instance, RMSE. I'm not sure how. I think this has been merged, but I'm not sure if it's on CRAN yet. I would have to check. But in any case, soon it should be possible. Perhaps on the GitHub version of Lou, it's already be possible. I'm not sure if the current interface of BRMS to Lou does allow that already. I think not. So as soon as that stuff is on CRAN, and if BRMS doesn't yet support it, feel free to open an issue to remind me to make this possible in BRMS.
Okay, perfect. That's it for now.
Yeah. So just one thing to add, using the Lou package and some functions of that manually, it's possible to have those other measures in place already, but the interface would be kind of a lot of manual hacking. So that should be over. So that should be changed quite soon. Good. Okay. So individually, our ELPD values don't tell us much, so we're going to compare them. And so we're going to compare them using the Lou compare function. So we're computing Lou for fitrand1 and for fitrand2. We're throwing that into the Lou compare function, and then we get this nice output matrix with the best fitting model on top. So basically the models are ordered by how well they fit. And we see so basically all models are compared with the best model. So the best model has difference to itself of 0. So the first row is 0. And we see the best fitting model is fitrand2, and fitrand1 kind of has an ELPD difference of -50. That alone wouldn't tell us much. But we see that the standard error of the difference is roughly 10. So it's, in this case, it's roughly 5 times a standard error. So we have quite some evidence that the second model, including also a two-dimensional spline and varying intercepts for the residual standard deviation sigma, is the better predicting model, according to ELPD and leaf one cross-validation.
From the chat again.
Yes.
How to interpret good and bad Pareto K diagnostics?
Yes. So everything below 0.7 is fine. Everything above that is dangerous. So you should aim to have no Pareto Ks above 0.7. And if you have some, there are 3 options. First of all, if there are just a few and the differences of your model are big enough, you're probably okay to ignore them. Please don't say you heard that from me. Yeah, so that's it's kind of unsafe to do that because you're ignoring warnings which may mess up your results. But of course, like that's a possibility if there are just a few observations compared to like a lot of other observations where it was fine. The other 2 more reliable options are, first, either do some manually refitting for the specific observations where the Pareto K was high, that is, do exactly for cross-validation for those. BRMS supports that using the ReLou function or the ReLou option in Lou. And we have recently implemented another way to get around kind of doing exactly one cross-validation, because that's obviously time intensive, and we call that moment matching. So that tries to kind of try even harder for important sampling to bridge the gap, and you can activate that in Lou using the moment_match argument. And this is also like implemented in recent versions of BRMS. Yes, I have seen a lot of people when kind of Lou failed to use other information criterion. So Lou can be seen as an information criterion just as WAIC or AIC. But please be aware, if the Lou IC throws high Pareto Ks, that means the assumptions that are implicit in AIC or WAIC are also not met. But those, like AIC and WAIC or like some other information criteria, usually won't have a diagnostic to tell you, but there will still be ill-posed if Lou throws an option. So just changing to WAIC or some other information criterion is no solution. They just don't have the diagnostic to tell you they are not reliable. But if Lou IC tells you it's not reliable, neither will other information criteria be that all approximate leave one hour cross-validation, such as AIC or WAIC. Okay, so in the interest of time, I would like to skip this kind of case study where I'm going through some like iterative model building. You will have it on YouTube. I will share the slides so you can go through that. So I will kind of wrap up so that we have like more time for like additional questions if there are. So if you want to learn more about myself, you can check out my GitHub page. You can write me an email if you have BRMS questions. Perhaps don't write me an email, but ask like in the forums I'm going to link to in a second. And if you want to check me on Twitter, I'm happy to be tagged as well. If you want to learn about BRMS, BRMS is on GitHub, of course also on Crown, but it's hosted on GitHub primarily. Since BRMS is part of Stan itself, it's also, we have forums on the Discord, Stan forums. You can check out the help pages. And if you don't know where to start at our help pages, BRMS has, I don't know, 7, 8 vignettes and growing, and you can access kind of links to them using the vignette package is equal to BRMS function in R. If you want to learn more about Stan, Stan has its own website, mcstan.org. And of course, you can also ask Stan questions in the Stan forums at Discourse. So that's it for me. Thank you very much for your attention. And yes, I'm happy you participated and asked so many questions. Thank you.